property of an inverse. So if I start out with an x and I send it through sine and then send that answer back through its inverse, it's going to come out unchanged. What's that? What's loud? You're having a hard time hearing me? Yeah. No, it's okay. Do you understand that loop?
I'm sorry, can you do it one more time? I'm sorry.
Give me any function, all right? Any function. Plug x into it.
Yep.
It's going to spit out an answer. Okay. The inverse function will always take that answer back to where it came from. Okay? So it starts out as x. X goes in to some function. And then that answer goes to its inverse. It comes out the way it started. So this was like the input. Okay? So you wrote this down.
Yes.
That's not what's happening. This is multiplication, not composition. This is composition, sine of sine inverse, right? Yeah. Yeah.
Well,
Let me see.
best shot.
Yeah, keyboard. Yeah, that's the whole thing. You got to try.
Yeah, so it's like we multiply with 2.
Okay.
So this half going to be here.
Yep.
So 2x equals to e to the y minus e to the negative y.
Mm-hmm.
And then we're going to multiply both sides with the natural log.
Mm-hmm.
Natural log of 2x equal y plus y.
So do you?
Is that the right direction?
Kind of. This line right here is not true.
Okay.
Okay,
So
it's not y plus y. But you're on the right track, but it's not y plus y. I know what you're doing, but the property you're using doesn't do that.
You want to give us a tip?
I'll give you a tip. Let me see what other people have first. Think about it some more. Did someone else raise their hand? I know this table, but okay. Where am I looking?
We got till here.
Yeah?
We just moved the 1/2 over, and then we were thinking about factoring.
Or adding natural y.
Okay.
But if we factor out like e to the y, you can't factor out because set e to the negative y.
Yeah, you would still have an e to the y here in some way. It would still be there. So not quite. Natural log might work, but you got to be careful with that.
Natural log of this whole side.
Yeah, something like that. Yeah, so let's just see if anyone else is getting close, and then we'll.
Okay, ready?
Y'all feel like y'all are getting anywhere on it? No? Okay. Over here, y'all feel like y'all are making any progress? Can I see what you're doing?
It's propped somewhere. It's like this.
Okay, now here you have it equal -1, right? And then what are you trying to
So
set
if I
them?
divide this out, then I can separate it into 2 separate fractions and bring the e to the y back over and maybe factor, but I haven't tried.
Y'all are the closest out of everyone so far, right now. Yeah. Y'all have anything here?
So I was trying to solve this side first because I'm not sure if I'm doing this right because you have the natural log.
Mm-hmm.
So can't this be written as x plus?
You're taking the derivative though.
Oh, okay.
Yeah, we're not taking derivative. We're trying to show that if you solve this for y, you get that. That's what we're trying to show. Okay.
Safe to say that I can get rid of the 1/2 and multiply both sides?
Yeah, you can multiply both sides by 2. Yeah. Okay, did y'all have, let me check the last table over here. Did y'all have any progress being made?
Oh, we'll use the book.
That's not fair.
Well, so when we first
It's a
started
resource.
out,
That's a resource, you're right.
what we first started out doing was
Yeah.
getting the 2 over to this
Yeah.
left side and then basically coming out with ln 2x equals 2y.
I knew we were going to have to take the natural log.
Let's
of
take the
both sides.
natural log of both sides.
That, you have to be careful with that. That step right there is not the next line. No. So that's where everyone kind of got stuck. Okay, I think we're at a point we can talk. All right, let's talk about this. Y'all ready? Okay, so what most of you did, which was correct, is to start out by just multiplying both sides by 2. And that will at least clear out the fraction, right? Like that. Okay. And then there was different approaches that I saw. Some people were like, hey, I can take the natural log on both sides. Let me show you the problem with that, all right? if I take the natural log on the left side, I get natural log of 2x. And if I take the natural log on the right side, I have to take natural log of the entire expression. Okay? And then you cannot just kill off each of these e's, because this is natural log of a difference, not natural log of a product. So we have all these properties of logs, but one of the properties we have is not this, okay? This is not a property of the natural log. Natural log of x plus y is not the natural log of x plus the natural log of y. In fact, the correct formula is this. Natural log of x times y is natural log of x plus natural log of y. In college algebra, we're taught if you have a product in a log, you can split it into two logs. This is called expansion and condensing and expanding log expressions. So this one's no good, this one is good, but we don't have this, right? We have natural log of a difference, and there's no way to pull that apart or rip it apart. So you'd be stuck here, okay? Now we will take a natural log, but not yet, right? So even though that was a good approach, it's not going to work. So something else I saw, or think I saw, was, well, I don't know if this is actually what I saw, but let me just show you the correct step, okay? So look at this. Okay, see that? Right, I mean, that is what it is, right? That is what it is. Okay, so what I'm going to do now is I'm going to clear the fractions, which means I'm going to multiply both sides of the equation by e to the y. Okay, so if I multiply this side by e to the y, I get 2x times e to the y equals, now what happens if I multiply that by e to the y? I get e to the y times e to the y, which is e to the 2y. And then minus, what happens if I multiply this one by e to the y? Cancels out and you just get minus 1. And now this is the part that's weird, all right? Just watch and see what I do here. Okay, brought everything over to one side.
Factor out. No.
Now you can't factor because this one doesn't have either y. So it looks like a quadratic. It looks like a quadratic, right? So if you squint your eyes just enough, do you agree that I can make this substitution? U is e to the y, right? Then what is this piece right here? That's really e to the y squared, isn't it? Because e to the y squared means you'd multiply 2 times y, and that's 2y, right? So let me rewrite this equation I have. It's 0 equals, what does this become? U squared, right? U squared. That's e to the y squared minus 2x times u minus 1. Right? All right, now you're used to seeing this. All right, I'll leave that on the board for now. But you're used to seeing this from college algebra and pretty much all of Cal 1 also. Is anytime you ever have a quadratic equation, you can use a quadratic formula, right? Right? So if you have a number in front of x squared plus a number in front of x plus a number by itself equals 0, then x will be this, right? But every time you've ever used the quadratic formula, a, b, and c have always been constants, haven't they? Well, not now. A here is 1. B here is actually what? Negative 2x is your b, and your c is negative 1. And we're going to use the quadratic formula. All right? So using the quadratic formula, this says that u, right, not x, because we're not using that. Our quadratic is a quadratic in u. So u will be equal to, what's negative b for us? What's negative b? What's the negative of the thing in front of our variable?
2x.
It's just 2x. 2x plus or minus the square root of, what's our b squared? For us, that's negative 2x, but squared. 4x squared. minus 4 times a times c. So that for us is 4 times a is 1 times c is negative 1 all over 2 times 1. Okay. Yes? All right, let's clean this up. This is just 2x plus or minus the square root of 4x squared minus 4 over, oh no, not minus 4, plus 4, sorry, all over 2. Okay, underneath that root, you see that those both have 4s? And so that 4 can come out of the root as a 2, right? So that I can pull the 4 out, and then that'll become a 2 plus or minus. The 2 came out of the root, right? Like the 4 came out, but it comes out as a 2. What's still under here? X squared plus 1 all over 2. Now, they all have 2's. Right? So where are we now? This was u equals. U equals x plus or minus the square root of x squared plus 1. Man, we are getting really close. Look at the answer here. We're getting close. Pardon? Yeah, well, yes, but we don't have a natural log yet. So when we get to that, I will address that. So now we have to remember, what was it that we were trying to solve for? Y. There's no more y's because we did a substitution, right? So what's u? What was u? E to the y. So now this is e to the y equals x plus or minus the square root of x squared plus 1. And now I have an equation. All I did was switch my u back to what it was. I have an equation. Here's y. Yes?
I was under the impression when you have like an addition or a subtraction, you can't cancel out like that.
No, it's okay. Because this would be 2x over 2 plus or minus 2 root x squared plus 1 over 2 if you split it, right? Okay. And then you could cancel. What's that?
You can also do it as it's factoring out of 2 and then cancel.
Factor out a 2 of the top and then cancel. Yeah, there's a couple of different ways to approach that. All right, so we're trying to get y, right? And we finally have like y just in single expression. So now you can get the y out of there with the natural log. So if we do natural log on this side and natural log on this side, the left side becomes y. Equals, and then natural log of x plus or minus the square root of x squared plus 1, which is almost this answer. This one is just plus, this one's plus or minus. So why are we not looking at the minus? Why are we not looking at the minus? So how do you know, if this is a minus, how do you know it would be negative? Like how do you know this would be negative? Okay, so we have to understand here that no matter what we ever plug in here for x, no matter what, this quantity is always bigger than that quantity. And the reason you know that is because what would it be right here? That would just be x, right? And that would be equal to that. So right now, this would be 0, wouldn't it? No matter what we plug, well, if we're using the minus, this would be 0. But if I'm adding a little more to that, then this quantity is bigger than that. So if I do that minus this, it's going to be negative. So I can't have that happen because of the natural log. So I can only look at the positive. And there we are. So that's probably, for most of you, the first time you've ever seen the quadratic formula used to solve an equation where your a, b, and c were not constants, where they're actually variables themselves. But you can still employ the quadratic formula for that, which is pretty cool. All right, so all we did, all that work, was just to show that the inverse hyperbolic sine function has a definition. So if you wanted to now know what the inverse hyperbolic sine of 4 was, you would just plug 4 here, and you would get an answer. Okay? All right, what do you think we should do next then? Should we come up with a formula for the inverse hyperbolic cosine? No, hell no, we're not doing that. Okay? But it would be a similar thing, right? It would be a similar thing. So in the book, there is a definition of this one. the hyperbolic inverse for cosine and tangent. What we're more interested in is their derivatives. So could we find the derivative of this? Yeah. How would you find the derivative of this?
1 over.
Yeah, you take derivative of that and use a chain rule, which is kind of what you were doing, right? So you do 1 over that, and then you have to do a bunch of stuff in there. But we're not going to cover it. It's the derivatives of those are on your sheet. Reference page 5, numbers 31 through 36 are the derivatives of the 6 inverse hyperbolic trig functions. So do you feel like you've been buried with trig formulas now?
Just to clear the air.
Yes.
Are you going to ask us to solve something like this on the test?
To derive one of these?
No. To prove it.
Like to prove this? Nah. No. That might be like a bonus question.
Okay.
Yeah.
I'm okay with that. So
Yeah. Yeah. Now, what I would ask you is something like this. I'm just grabbing one here. If y equals x sine hyperbolic inverse of 1/3 x minus the square root of 9 plus x squared, find y prime. So that is a problem out of the book. That's a homework problem. I have not shown you anything like this, right? What I have shown you is that I have told you, there is a formula for the derivative of the inverse hyperbolic trig functions, right? So now you get to bring all that stuff from Cal 1, your product rule, chain rule, quotient rule, all that stuff is in there, but now you've got these new functions, and now we need to figure out if we can determine the derivative of this. So if we go through this, we have to first recognize we have subtraction, right? So we can take derivative of this one separate from this one. And then over here on this one, we have a product, which means we have to do our product rule on that first expression, right? So let's go ahead and crank this one out. Our product rule says we'll do the derivative of the first one, which is 1, right? 1 times this. I'll go ahead and put the 1 there. 1 times the hyperbolic inverse sine function of 1/3 x. Right, so that's the first part of the product rule. Plus, now what? The derivative of this, right? Okay, the derivative of that. And I haven't put that on the board, have I? But I've told you where it is. So now you go to reference page 5. And you look at formula number 31. And it says here that the derivative with respect to x of the inverse hyperbolic sine function is, I can't read that. Yeah, there's no negative on there. There we go. Is that. That's the derivative. Okay? So now we use that. So what would the derivative of this be? Okay, be real careful. What's the derivative of this going to be? 1 over the square root of 1 plus 1/3 x squared, which is 1/9 x squared, right? We'll go ahead and just square it now. 1/9 x squared. You have to square the 1/3 also, right? Question?
So it's the same as
Not quite. No, there's a plus here. Yeah, slight little differences. I mean, they're little tiny differences. I almost mentioned that. I was almost going to mention, look how close these are, but I didn't. Should have. All right, so very close, but not the same. All right, so are we done with the derivative of this?
Now we're going to take the chain rule.
Yeah, chain rule. You have to take derivative of the argument. And derivative of the argument here would be just 1/3. So I'll just tack that on here, 1 over 3. Are we done with the derivative of that first part? No, what do I still need there? I need x to finish off the product rule. So that is your product rule, right? That is your product rule right there. Yes? Just that. Now we still need to do minus derivative of that. So minus, now this right here, you know, this is really like Cal 1. I mean, let's just do a show of hands. I really don't know if we're going to use these clickers. They just seem kind of useless. How many of you in Cal 1 would do this problem this way and do like 1/2 and then do that to the negative 1/2? Okay, that's fine. I know my former students, my Cal 1 students aren't going to do that, right? Y'all are just going to do 1/2 root of 9 plus x squared. So like that's the way I teach it. So depending on how you learned it, it's the same answer. Okay, if you bring the 1/2 out and do that to negative 1/2, it's the same thing as this. All right? It's just, to me, it's a little faster if you know that the derivative of the square root of something is 1/2 square roots of that something. So that, to me, is just an easier formula, personal thing. Okay, so the derivative of this is this, but I'm not done, right? Now I need what? Times 2x, the derivative of the radicand, what's underneath the root, so 2x here. And these 2's cancel. So this is our derivative. It ain't pretty, but it is what it is, right? Sorry, I was thinking. Okay, that's our derivative, right?
Yep.
Uh-huh. Yes?
Is that simply this? Can you get this simplified out or just the exact answer?
I think this is fine. Yeah, I think that's fine. We could start really messing with this to see about making it, like, look at this 3. Look at this 3 right here. If I take this 3 and I push it into the root, what happens to something when you push it into a root? It gets squared on the way in, right? So if I take that 3 and push it in, that 1 becomes a what? 9. And then this right here becomes 1. And then look at those last 2 terms. They cancel. Right? So you may not see that. So I wouldn't count this wrong if you gave me the answer without doing that. But as you can see, the answer to this is pretty nice. That's the answer.
What about extra points if we solve it?
I would make a notation next to your name, and I would be like, yes, this is good. Okay. Yeah? So if you take kind of the totality of what we've done today and what we did kind of last time, I've tried to introduce you to a bunch of new functions and all of their derivatives and telling you they exist. And now, after I say that, I can ask you to take derivatives, and you have to incorporate these into everything you learned in Cal 1, right? So in the homework, you'll have an opportunity to practice this. All right. Let's see, what time is it? We still have 15 minutes, okay. Let's do this problem here. By the way, that problem that we just did, the author of this book made that function. They designed it in a way that when you differentiated it, you got that nice answer. Like they did that on purpose. They wanted it to give you a nice answer like that. What's that? Yeah, exactly. Okay, so here's the problem I'd like for us to kind of finish off with here today. Let's say that we have 2 poles. And let's say that they are, we're going to kind of orient this as if it was an x and y axes. And I'm going to tell you that this pole is like 7 meters away, 7 meters away. So there's 14 meters between these 2 poles. and then there's a wire hanging from this, all right? And of course, if you imagine that wire, if we would continue it, would be that shape. And I already told you that that's going to be a hyperbolic cosine function, right? And I'm going to tell you exactly for this wire what it is. It is y equals 20 cosine hyperbolic of x over 20 minus 15. Meters. Meters or miles. It doesn't matter what we're talking about here, but we'll say meters for now. Okay, so this is the function that would give you that graph. All right. So here's the question. If you imagine this like kind of tangent line there, I want us to find theta. The angle between the wire and the pole at the point that they meet, right? I want to find the angle between the wire and the pole at the point at which they meet. So what is it that we need to find then? Like if we call this, let's call this thing not y, let's call it f of x. What is it that we're actually trying to do here?
And the slope.
We're trying to find the slope of the tangent line to this curve at what? At what point? We're trying to find this.
The point where the wire meets the pole.
Okay, which for us corresponds to 7, right? This is our x-axis. So at x equals 7. So we want to know this. We want to know f prime of 7. Now that will give us the slope of the tangent line, right? Is that the same as theta? We'll have to think about that a little bit. But for now, let's just take this part. Let's find the slope of the tangent line, then we'll see if it's theta or not later. So can we take the derivative of this function? We're going to need that, but let's start with this. What is the derivative of this function? All right, well, you have 20 attached to the front of the function, right? So it's going to just come for the ride? What is the derivative of cosine hyperbolic of something? Sine hyperbolic, but not negative sine hyperbolic, right? This was the weird one. So this is just sine hyperbolic of the something, right? Are we done with the derivative of this? Chain rule. We need derivative of what's inside also, which is, no, because this is the same as 1/20th x. So the derivative of that would be 1/20th. So I need to tack that on to the outside of this. That's actually going to cancel that out, isn't it? Okay, kind of got lucky there. Now are we done with the derivative of this? This part? Yes, and then minus derivative of 15, which is 0. So that's it right there, right? This is it. It's sine hyperbolic of x over 20. That's the derivative of the function. But we want to know the derivative of the function at 7, right? So now let's go back up here. I need to know what sine hyperbolic of 7 over 20 is, right? So now use the formula for sine hyperbolic, which is up there, top left. This is 1/2 e to the x. What's x for us? 7/20 minus e to the negative 7 over 20. Right, and so we're going to definitely need our calculator for that. And I think I brought the wrong calculator, so I'm going to trust a couple of you to get the answer on that. We're going to round it as a decimal. We're going to get a decimal and just round it. So this is going to be an approximation. It's approximately we'll see if we can get like 3 students to get the same answer. Don't forget your quizzes are due today. Those little take-home one things, right, that I asked you to fill out. It doesn't like it? Let me see. Error. It might be you're using a minus versus a negative. Did you use negative or did you use minus?
Minus. 'Cause
So, yeah, when you use your use the minus key here and a negative key here. What did y'all get?
Oh, my bad.
0.357. We have a couple of students that got that? Okay. So is that the angle or not? This is not the angle. This is the slope of the tangent line. So imagine, if you will, that we take this point here, and let me just kind of zoom in on it, okay? We're just going to kind of zoom in. Here's our point. Our curve's coming in here. We have our tangent line that was going like this, right? We have our pole that goes like this. We're trying to find this theta, right? All we've found is the slope of this line. So let's just do this. Let's do a little construction here. Imagine that this is a right triangle. What we have found is that this number represents the rise over run, right? So if I call this 0.357 as my rise, and I call this side from here to here 1, then this angle, I'll call it alpha, right? The relationship here is that I know that tangent of alpha is this over this. Do y'all buy that? Y'all buy it or not? So I'm saying, look, this blue line has that slope. I use the slope definition that it's rise over run to create a triangle where my rise is 0.357 and my run is 1. That way when I take the ratio of this, rise over run, I get that number. And now I know that I can recover this angle alpha by just doing the relationship that tangent of alpha is this over this, which is 0.357. So how do you get alpha then? Arctangent on both sides. So arctangent on both sides. And do this on your calculator and do it in degree mode. Let's get our answer in degrees because it'll be easier for us to put our heads around it, I think. Yep. Because alpha is not theta. These two angles aren't this.
Can you just use a triangle beneath it?
You could do, yeah, you could do the same. Yep. I just thought it would be weird if I started my triangle down here and did rise over run. Yeah. So we'll ask ourselves, are alpha and beta the same thing? Are they or are they not? What is alpha? So on the calculator in degree mode, 19.6? About 19.6 degrees? Okay. No? You got 19.6? That's 2 people? 3 or 4? Okay. So is alpha theta? Is alpha theta? It is not. So here's how to see that, because let me just draw this vertical. Look at this right here. Theta is this angle, right? Between here and here. That angle right there is not this angle here. It's actually that angle right there. Okay, so this goes back to some geometry. If you have 2 parallel lines, right, like this, then if you have a bisector, you have alternate interior angles are congruent. This is going beyond what we need to think about, but yes.
Technically, like, alpha would be on top of theta.
On top of it. Oh, like up here?
No, like, right, like, if you went to theta, it would be
Right here. Yeah, oh yeah, there's so many ways you can look at this. You can do like there to there, and then you could do like there to there. You could do, this is alternate interior, so alpha's here. I mean, there's all sorts of ways to visualize this. The important thing is that you understand that when you have the slope and you go recover the angle, that's not the angle you were looking for. Okay, the angle we're looking for is theta. We have alpha. So we know that this is 19.6. And we know that all these angles have to add up to be 180. So 19.6 plus 90, subtract from 180. What do you get? What is it? 70.3-ish degrees. And this is like an approximation, but. Question? What?
So how did you get 7.3?
Because you know this angle is 19.6. This is a right triangle, so you know this angle is 90. And they have to all add up to be 180, right? The sum of the angles of a triangle is 180. So do 180, take away 19.6, take away 90. Yes?
We should just like assume that has to be rectangle. Where alpha plus theta would have to be 90, so you just do 90 minus the 19.6.
Sure. Yeah. Yeah. I mean, it's however it makes most sense to you in your mind is the way you should do it. I mean, right? Most students are going to sit here and say that, you know, all the angles add up to be 180. So you just add them all up, you know, solve for the unknown. Or you just say, okay, that's 90, so I know those two together have to be 90. So take that away from 90. Yeah, I mean, it's all the same, right? We're all going to come out the same thing. Okay. Let's see how we're doing here. So on Monday, we'll start antiderivatives.
That's what I thought you were doing today.
I'm kidding.
That's what I thought you were doing today. So I'm like, what?
Yeah, no, Monday's a holiday, everyone. Y'all know that, right? So Monday is a holiday. I won't be here. You should not be here either. And we'll pick up on Wednesday, and we'll start up with antiderivatives. So we actually get into the Cal 2 starts. Okay, quizzes, please just leave them here on the corner of my desk. And have a good weekend, have a good holiday. You should be able to do all your homework for 3.5 and 3.6 now.